All right, so tonight we're going to be talking about graphing square root and cube root functions. So first, let's take a look at some tables um, and compare some tables for looking at some different functions. So in this first column, I've got x squared function, and here's the table for x squared. And I want to compare it to the square root of x. Now, if you remember, x squared and square root are opposites of one another. When we're solving equations, that's how we do the opposites. And so let's look at what their tables look like in comparison to each other. Now, I'm going to ignore the ones with decimals, because decimals just make my life complicated. So if I'm just looking at the ones that don't have decimals, I notice that 0, 0, and 1, 1, they match. Those are exactly the same. When I get down here to 9 and 3, what I notice is that that goes with, oh, it's the same two numbers together. 2 and 4, oh, that goes with 4 and 2. And honestly, the pattern there, if you notice, it's the same two numbers, but they've swapped places. Well, that can hold true for these as well. 0 and 0, they could have swapped places. We just couldn't tell because they were the same number. And 1 and 1 may have swapped places. We just can't tell because they're the same number. Let's look over here at cubed and cube root. Again, they're opposites of one another. So let's look and see what happens. Again, I'm just going to kind of ignore the decimals because decimals just make things unneeded complications. But again, 0, 0, matchy, matchy, -1, -1, -1, -1, also matching, 1, 1, and 1, 1. Now here I've got -2, -8, and over here I've got -8. Again, same two numbers, they've switched places. 2 and 8, 8 and 2. Same two numbers, but they've switched places. So these functions we know are opposites of each other, but we know the math term for that is inverses of each other. By definition, an inverse means that the domain and the range switch places. So these functions do go together. Their x's and their y's are just switching places. So it's the exact same set of numbers. Well, if we're using the exact same set of numbers, but the x's and the y's are switching places, what is that going to do for the graphs? Because we know what the graph of x squared looks like. That's a parabola. That was a parabola. And if you don't remember, x cubed is a parabola, but one half of it goes up and one half of it goes down. You know, that's what those graphs looked like. So if we know that these graphs use the exact same set of numbers, but we've switched x and y, what is that going to do for their graphs? So let's take a moment and look at it. Let's plot the points. So if we took the different points there and we plotted them, this is right here is the x squared. Now on that table we only had half of the parabola, so that was the x squared graph. And then here is the square root graph. Here are the points from the square root. So that means those are actually the same shape, but this one's turned sideways and this one's going up and down. If we look at the cube, we know cube was the one that looks like this. There we go. That was the cube graph. And cube root, if we look at these points, ends up looking like this. Again, same shape, but turned on its side. If you remember from our transformations, there was a rule that told us to switch x and y. And the rule for switching x and y was to do a reflection over the line y equals x. And when you do a reflection over that diagonal line y equals x, that's when you switch the x and y points. And so that means that these graphs, the square root graph and the cube root graph, are just reflections of the square graph and the cube graph. So as a result, the graphs have the same number of points, or the same numbers as their points, but the x and y have switched places. This means that they are the same shape, they just have to be reflected over the line y equals x. So these are graphs that we know, they're just reflections. So if this is the original parabola, and I reflect it over that diagonal line y equals x, this is the parabola that I get. It's a sideways parabola. But you may notice that there's a problem with that. We want this to be a square root function. The big rule for functions is that they have to pass a vertical line test, and this one is going to fail it miserably. It does not pass the vertical line test. It touches it in two places. That's because if I take a square root of a number, remember, it could be positive or negative. The square root of 4 could be positive 2 or it could be negative 2. And that's two outputs for one input, and that makes it not a function. So what we have to do is we have to define the square root function as being the absolute value of x. Now, that's really a fancy way of just saying we're always going to take the positive square root. So when we're dealing with the square root functions, if I take the square root of a number, I'm going to take the positive square root. If I want it to actually be the negative square root, I would have to put a negative in front of it, and that would tell me to take the negative square root. So we're going to define the square root function as just being the positive. And if we do that, that means we're just taking the top half of that parabola. So the square root function is just going to be the top half of that square root, or of that sideways parabola. So the result, the function square root of x ends up being this half of a parabola. So important to note that its vertex, its basic vertex is at 0, 0. Its end behavior on the right, okay, on the right as x approaches positive infinity, y is also approaching positive infinity, and x doesn't approach negative infinity. In fact, its left behavior is that it ends. As x goes to negative infinity, it can't. It stops. This one does have a restricted domain. It has a restricted domain because x has to be greater than or equal to 0. Not all real numbers. We can't take the square root of a negative number. That's what that boils down to. Now, its range is also going to be limited because notice we took away that bottom half of the parabola. So that means that its range is also going to be from 0 to infinity because it's starting here at 0 and it's going up. Square root function is also no symmetry. It's not symmetrical. The parabola has two sides to it. Well, we took away its symmetrical side down here, so it's top heavy. It is not symmetric. However, it does follow the same pattern as our parabola. The only difference is we're going to change what goes up and down and what goes left and right. If you remember, for a parabola, we would start at our vertex, and if I went over 1, then I would go up 1 squared. If I went over 2, then I would go up 2 squared. It's going to still be this pattern, but we're going to switch the up and the over. So now if I go up 1, I'll go over 1 squared. If I go up 2, then I'll go over 2 squared. So I go up 1, I go over 1. If I go up 2, 2 squared is 4, so I go 1, 2, 3, 4. It's the same pattern, we're just turning it on its side now instead of putting it up and down. Now the cube root function. This was the original cube function, and if we reflect it over this sideways line, we get this sideways cube function. And as far as being a function, it is. I can vertical line test this all day, and it's only going to cross the line in one spot. So it has no problems. We don't need to redefine it. We don't have to worry about not passing the vertical line test. So it's as good as it's going to get. We get to keep both sides of this graph. So let's look at its characteristic functions. We do have a vertex still at 0, 0. That's the basic. Its end behavior, it does have arrows on both ends, so it doesn't stop. It is a keep on trucking kind of thing. As x approaches the left, the negative side, y also approaches the negative side. It goes down. And as x is going off to the right, y is also going up. It's positive and positive. So it does have end behavior that keeps going. Its domain is not restricted. It can go left and right. I can take the cube root of a negative number. If you remember, the cube root of -8 is -2. We can do cube roots of negative numbers, so it doesn't have the drama. The range is also all real numbers. It has no restrictions because, again, if I take a cube root of a negative, I get a negative. Take a cube root of a positive, I get a positive. So that just includes all of the numbers. It has a rotational symmetry, but it doesn't have a folded in half symmetry. But if we take it at the vertex and rotate it, it would line up with itself. So it does have rotational symmetry when we talk about our transformations. And it also follows the same pattern as the cube and the square, but turned on its side. So when I go up 1, I will go over 1 cubed, just like when we did with the square. 1 cubed just happens to be 1. If I go up 2, then I will go over 2 cubed. So up 2, go over 2 cubed is 8. 1, 2, 3, 4, 5, 6, 7, 8. There we go. So that gives us our points there. We do have to remember, though, unlike the square root that just had 1/2 of it, the cube root does have a negative half to it. So if I go down 1, I'm going to have to go left 1 cubed. And if I go down 2, I'm going to have to go left 2 cubed. So down 1, left 1, down 2, 2 cubed is 8. 1, 2, 3, 4, 5, 6, 7, 8. There we go. So that gives us our pattern for the cube root. Now, how can we use our transformations to help us to do these graphs? Things that we want to remember. The vertex doesn't have to stay at 0, 0. So if I want to move it someplace else, just remember inside the function moves it left and right. So if I add, I will go to the left, and I subtract, I will go to the right. If I go outside, that can move it up and down. Adding moves it up, and subtracting moves it down. So it's still going to be our same rule for the vertex. Your vertex is always going to be opposite of the inside number. That gives you your x-coordinate. Keep the outside number. That'll give you your y-coordinate. So the opposite of the inside number, keep the outside number. Reflecting, though, we need to be careful. We didn't have to worry about left-right reflections or reflections over the y-axis when we were doing symmetrical shapes because they were the same on both sides. But these two shapes don't have reflective symmetry. And so if I flip them up and down, that changes them. And if I flip them left to right, it changes them. So things that we want to remember about transformations for reflection, if I want to flip it over the x-axis, if I'm flipping it over the x-axis, then I'm going to put the negative outside the function. But if I want to flip it over the y-axis, if I want to flip it left and right, okay, I'm going to do the negative inside. And that's not subtract, that's multiply by a negative. So again, to flip it up and down, because up and down things always happen outside the function, I would multiply it by a negative outside the square root. So something like negative square root of x or negative cube root of x. But if I want to flip it left to right, if I want to flip it over the y-axis, then the negative would be inside the square root. So I would have the square root of negative x or the cube root of negative x. And this would flip it left to right. So not only can we flip it up and down, we can also flip it left to right. Dilating is also still going to be the same. Remember, we're talking about stretching it vertically or shrinking it vertically. We can still multiply by numbers out front, outside the function. And so this will give us a graph that we've stretched. So all this is going to do is it's going to change our up number. So instead of me going up 1 and over 1, I might go up 2 and over 1. Or instead of going up 2 and over 8, I might go up 4 and over 8. Notice it does not change the over number. It just changes the up or down number. Multiplying outside, we can dilate. So let's look at some examples. All right. So it's a square root. So I know the shape. It's a square root. It looks like this. All right. I know where my vertex is going to be because I do the opposite of the inside number, keep the outside number. So this will be at 3, 0. So 3, 0 gives me a vertex right here. It's not being stretched, and it's not being flipped. Excuse me. So now I can just follow my pattern. My pattern for square roots was to go up 1 and over the square. So 1 squared. Up 2, over the square. All right, so I'll go up 1 over 1. Go back to the vertex. If I go up 2, I have to go over 4. Could do 3, but I don't think it's going to fit. Up 3, I'd have to go over 9, but that runs off the edge over here. And so this gives me, and it is a parabola. You want to make it kind of curvy as best you can with your, it's not a straight line. So you want to make sure that you're making it look like a half of a parabola. And that's all I can get to fit on the graph. Now, this one is a cube root. So right away, I know that my shape is this shape. So that's my shape. I need the vertex. So opposite of the inside number, which is 0, keep the outside number, which is 4. So 0, 1, 2, 3, 4. That gives me my vertex. There's no negative, and it's not being multiplied by anything, so it's just its basic shape. So we remember that if we go up 1, we have to go over 1 cubed. If we go up 2, we have to go over 2 cubed. So up 1, over 1 cubed, which is just 1. Up 2, got to go over 8, because 2 cubed is 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, we also need to remember that the cube root has that backside to it. So if I go down 1, I go back 1 cubed. And if I go down 2, I go back 2 cubed. So down 1, back 1. Down 2, back 1, 2, 3, 4, 5, 6, 7, 8. And so that gives me half going this way and half going that way. And this pattern is the same all the time. Let's check out the next one. All right, so it's a cube root. I know my shape. It's going to go this way. My vertex, well, it didn't get anything added to it, so it didn't shift anywhere. Its vertex stayed at 0, 0. It did, however, have a negative on the outside. And this negative on the outside is going to flip it up and down over the x-axis. So if we think about what this is going to look like flipped over, this top part is going to flip down, and now it's going to be the bottom part. And this bottom part is going to flip up, and it's going to now be the top part. So it's getting flipped. But it doesn't change what my pattern is. I'm still going to go, if I go up 1, I just need to now know that the top part is going over to the left. So I'm still going to go 1 cubed, though. That part stays the same. If I go up 2, then I'm going to go back 2 cubed. So I'm flipping it over. Notice this is why I kind of drew a little picture over here so I would think about what flipped would look like. So now instead of the top half being on the right, the top part is on the left. So if I go up 1, I go over 1. If I go up 2, I go over 8. 1, 2, 3, 4, 5, 6, 7, 8. Down 1, I go back the other way. Down 2, 1, 2, 3, 4, 5, 6, 7, 8. So this gives us that flipped effect for that cube root graph. Now, number 4, it's a square root, so I know I'm dealing with that shape. Nothing was added or subtracted to it, so its vertex is still at 0, 0. But I have a negative inside. And so this means that it's going to be flipped, but it's going to be flipped around the y-axis. So that means instead of flipping down, it's actually going to flip over here, and it's going to go this direction. But it doesn't change its pattern. If I go up 1, I'm just going to go left 1 squared. If I go up 2, I'm going to go left 2 squared. So up 1 to the left 1, up 2 to the left 4. I might be able to actually fit 3 on here. If I go up 3, I would have to go left 3 squared. Let's see if it would fit. 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. It did fit. There we go. So I can draw my parabola. But because it had that negative on the inside, it flipped over the y-axis, so that's why it came to this direction instead of this direction.